All right, guys. So I had a request to talk a little bit about benzene and its shape and its reactivity, which is covered on pages 478 to 480 of your textbook, I believe, in section 10.1. So I feel like maybe there's some maybe gaps or stuff that's been forgotten from topic 4, which talks about structures and bonding. So the first thing I want to talk about is just how the shapes of a molecule around a carbon atom can sort of be predicted by the bonds that are present. So we've kind of got three shapes that a molecule might make around a carbon. Okay, and we're going to focus in on really simple molecules to start, and then you can kind of think about how that might fit into a bigger molecule. So we've got this situation with 4 single bonds. We've got this situation with 3 single bonds and 1 double bond. Okay. And then we've got 2 situations that lead to the last one. We've got 2 single bonds and 2 double bonds. Let's put an and here. Or we've got 1 single bond and 1 triple bond. Okay. So these represent our different numbers of bonds around a carbon atom. And then that leads to different shapes. Okay, so if you have 4 single bonds around a carbon atom, that gives what we call a tetrahedral shape. Okay, where you have a carbon in the middle, and then you have bonds all making angles in 3D space, it's 109.5 degrees between each bond. Okay. And IB does kind of make a big deal about you memorizing those, so it's nice that you're not writing your IB exam, so you don't have to necessarily have that memorized. Okay, and if, like, my picture here is not super clear, and you may not have learned that wedge and dash notation before, so I do encourage you to maybe Google tetrahedral molecule and look up like a video or a GIF of it so you can kind of see it moving around in real time to get an idea of exactly what this shape means. Okay, unfortunately I don't have a molecular model kit here, otherwise I would build a model and I would show you that way, but a quick Google search will get you a better 3D representation of a tetrahedral molecule. Okay. Now our second scenario here is 3 single bonds and 1 double bond, and that makes the shape is called trigonal planar. Okay, so hopefully you remember this a little bit from your Vesper theory stuff in topic 4. Okay, so this is when we have, I guess this would be considered 2 single bonds and 1 double bond. That maybe is a better way to describe it. So this is when we have carbon and it's making a double bond and 2 single bonds. Okay, and in this case, we're actually only using one plane of the molecule. So I can sort of represent all the bonds lying in the same plane. Whereas with the tetrahedral one, I use this wedge and dash notation to show bonds coming out of the page or going into the page. Here, all of these bonds are lying right up against the page. So it makes like a nice flat triangle, and the bond angle is 120 degrees. Okay. And then our last scenario is a linear molecule around carbon. Okay, so this is either if carbon has double bonds on both sides, or, so that's, I'm getting a little bit mixed up with what the difference between what's called a single bond and a sigma bond. So that would be this scenario right here. So you can take the 2 single bonds out of there and you can call it just 2 double bonds. So this would be like our carbon dioxide molecule, which we know to be linear. We also get a linear shape around carbon if we have just a triple bond and a single bond, okay? So something like this. So if you had, anytime you have an alkyne, that carbon that's participating in the triple bond is making a linear shape in that part of the molecule. Okay, so this is just like a quick review on the different shapes that we might see around a carbon. And then these different shapes can lead to different things happening in our molecules. So for example, when you have a tetrahedral shape, that's why when we draw like an alkane, we draw it like this. Okay, because these sort of kinks in the chain are supposed to represent those bends that come from the carbon having a tetrahedral shape around it. Okay, so that leads to that way of drawing our carbon atoms. Okay, and then our trigonal, our situation where we have a double bond, that's what leads to like cis-trans isomers, because the double bond prevents any sort of rotation from happening around that double bond. So we don't get flipping back and forth, so it really matters what's on, or the relative position of things on the carbon. Okay, so hopefully you remember looking at cis-trans or EZ isomers. Okay, so how does this tie into understanding the shape of benzene, you may ask? Well, hopefully you remember, or you have seen, that benzene has the formula C6H6. And rather than that being just a straight line, a scientist called Kekulé came up with the idea that this is actually a ring. Okay, so you've got your 6 carbon atoms organized in a symmetrical ring. My ring's not going to look that symmetrical, but it is. Okay, and they're all held together. And then each carbon atom has a hydrogen on it. So that's how I get the H6. And then to make sure that every carbon has a satisfied octet, because right now each carbon only has 3 pairs of electrons around it, they want 4, we put double bonds in alternating positions. Okay, and then that gives us a Lewis structure for benzene that makes sense along with the chemical formula. Okay, now you'll notice that this right here, so if I focus in on just one of my carbon atoms, it's this in my table up here. Okay, so each carbon atom is trigonal planar. It's making it has basically 3 bonding pairs, 2 single bonds and a double bond. Okay, so 2 single bonds and a double bond. Okay, now the next thing I want to talk about is how the orbitals on carbon create that shape. Okay, and this is something that I believe it ties in a little more with the higher level content, which is why it might not feel super familiar to you when you read it in your textbook. So I'm going to give a brief intro style discussion of how we get that. Okay, so we're going to focus in on this one carbon atom. And the way it works, to make these bonds, carbon has essentially 3 bond orbitals that it uses to make the single bonds. So we've got this one right here, okay, and then we've got that overlaps with the other carbon, and then we've got this one right here that overlaps with the hydrogen, and then we've got one more bonding orbital that's like that overlaps with that carbon. So if I'm sort of numbering carbons, this is my principal carbon here, and this would be like 1, 2, and 3. So we've got 1, 2, and 3 here. Okay, so these bonds are formed by the overlap of orbitals. Okay, and so this bond, and this bond come from these overlapping orbitals that are all lying in the same plane. Okay, so that covers this bond, and one of the two bonds that makes up the double bond. That last bond, though, that second part of the double bond, it comes from what we call an unhybridized p orbital. You'll learn about this again in university if you need to, but basically there's this remaining orbital that comes out the top and the bottom of this carbon. Okay, so that's our last orbital. And rather than sort of lining up between the two nuclei, like we see this first bond in our double bond doing right here, the way that this bond works is it actually has overlap above and below the plane of the molecule. Okay, so this carbon right here can overlap with the orbital of this carbon right here, and that's what creates the second bond to make our double bond. Okay, and then there's some terminology that they were throwing around in the textbook. These bonds that happen between the two nuclei, they're called sigma bonds. Okay, and that's a Greek letter sigma to represent them. So this is a sigma bond, this is a sigma bond, this is a sigma bond. But then those bonds that happen above and below the plane of the molecule, like this one right here, that's called a pi bond. Okay, and you'll notice there's kind of a parallel here. Sigma bonds are often involve s orbitals, not strictly true, but often they do, whereas pi bonds often involve p orbitals. Okay, so tying that back to our electron or atomic structure stuff. Okay, now the last little thing about the structure of benzene, what observations tell us is that actually, if this were a perfect Lewis structure for benzene, we would see that these bonds, the double bonds, would be slightly shorter and slightly longer than the adjacent single bonds. Okay, so like this bond right here would be a little bit shorter because it's a double bond than this bond right here. But what's actually observed is that benzene is a perfectly symmetrical structure where all the bonds are equal in length. Okay, so the way that we explain that is each of our carbons have these p orbitals that create those pi bonds to make the double bonds. Sorry, my drawing here is not beautiful. You can definitely look up some better graphics. Even in your textbook, you'll see nicer ones. But I'm just trying to show these pi bonds here. Okay, so each of my carbons has a double bond, or it has that p orbital, and it creates that overlap to make the double bond. But actually, there's no reason that we can't have all of those p orbitals overlap in a ring. Same with the ones that line up along the bottom. Okay? And so what we actually observe with benzene is that it's a perfectly symmetrical structure where all 6 of those p orbitals are overlapping, and they are delocalized. Okay? So the electrons can travel anywhere throughout the molecule in this network of p orbitals. Okay? And that is why we often see benzene represented like this, a nice hexagon with just a ring in the middle, because this represents the delocalized electrons. Okay? I don't know if that video was helpful or if my weird scrawling just made things more confusing, but I do encourage you to read those pages of the textbook in section 10.1 about benzene. I believe it's page 478 to 480. And then there's also lots of videos or animations of this on YouTube. I made my own video because I know sometimes it's helpful to hear a familiar voice, but feel free to look up and even share other videos if you find good ones. Thanks so much.